So we'll start with what we known or what we call as a vector space. So yesterday, in the last class, I gave you some idea of what a vector space is, or like how do we actually create a vector space. So essentially, we take some operation. We take, let's say, some operation star. We used to take operations in group also, right? So you can just think for right now that there is, say, let's some operation star, okay, that you operate on a set V cross V, okay, and that the result is again going to be in V, right? So basically what star will do, that it will take two elements, okay, and it will map it to some other element in the set itself. So this V1, V2, they all belongs to V, and this W1 also belongs to V. So we can say that the image of this V1, V2 with respect to the operation star is actually W1. So now we are going to actually formally define it. What is actually a vector space? So a non-empty set is said to be a vector space over a field F. So in this case we are going to take the field as R, because you guys are in 4th semester, so I don't know whether you have studied field theory or not, but nevertheless you can assume that the field is R, right? So if there exist maps means functions, okay, so functions or operations, whatever we can call. So if there are functions, so we are going to define two functions here, okay. So earlier in group theory or in whatever we used to learn, we generally used to take only one function or only one map, right? But here we are going to define two functions. So the first function, we denote it as plus, okay. So it is a function, it will take some value of this V cross V and it will map to V, right? And it is defined as plus of x comma y is x plus y. This is called addition. And the second map that we are going to define is basically a dot it's going to be a dot, and this will be defined from R cross V to V, defined as alpha comma x. So dot of alpha comma x is nothing but alpha time dot x, and this is called scalar multiplication, right? So what we did till now is that we took a non-empty set V, okay, we took this non-empty set V and we have defined two operations on it. One operation we are calling it as addition, and what it will do, that it will take some element of V cross V, x comma y, and it will map to x plus y. And other operation that we took is the scalar multiplication, and what it will do is that it will take one element from this R, this alpha is from R and this x is from V, and it will map to alpha dot x. With following properties. So while studying group or ring, whatever you have studied till date, so whenever we define a map or whenever we define a function on any set, so we always seek out some properties, right? We always check that whether it is satisfying some properties or not. On based on that, we call it that okay, if it satisfies these properties, we will call it a semi group. If it satisfies this property, we will call it as a group, and if it is commutative, then we will call it as abelian group. So the thing is that we check whether how many properties it's going to satisfy, and based on that we kind of give them different names. So in this case we are going to see actually a total of 8 properties. So the first one is called commutative. And actually it is very easy. Commutative means which can commute, that is x plus y is equals to y plus x, right? Now the commutative is with respect to plus, right, because the operation here is plus. Then we have associativity. Now what does it mean? That it says that you first take x plus y, okay, and then add z, or you take x in last and you add y plus z in first and then you add x. Both things are going to be same. The third property is identity existence. So in group also we have an identity element. Similarly here also we are going to have an identity element. So the identity existence, so the thing is that there is some element 0 that belongs to V such that x plus 0 is equals to x is equals to 0 plus x for all x belongs to V. So if some element satisfy this property, we call it as the identity element, and normally or generally the identity element is denoted by 0. Then similar to group we have inverse existence. Now what does it mean? That for every x that belongs to V, there exists some y belongs to V such that whenever I add this x to this y, I should get the identity element which is my 0, okay, or y plus x. So it doesn't matter if I do x plus y or y plus x, I should always get the 0 vector. And this y is denoted as minus of x for simplicity. Okay, so we don't write actually, we say that the inverse of x is minus of x. We don't actually say that there exists some y such that x plus y is equals to 0 vector. So we don't say it. So for the sake of simplicity, we just say the inverse of x is actually minus x. Then number 5. So these 4 properties are with respect to which operation? With respect to the addition operation, right? So right now we have used just this operation, but we have defined one more operation, that is the scalar multiplication, this one. And now with respect to this operation, we are going to define some more properties. And the properties are that alpha dot x plus y must be equals to alpha dot x plus alpha dot y. Number 6 is alpha plus beta dot x is equals to alpha dot x plus beta dot x. Number 7 is alpha beta x this should be equals to alpha times beta dot x. And number 8 is actually 1 dot x is equals to x. Okay, so this 1 is identity with respect to the dot operation. Now here obviously note that this x, y and z, these are the elements of V, the set V, and this alpha beta, they belong to actually the field F, or in this case we have taken the field as R. So this is a particular field, right? R is a particular example of a field. So in general we can define a vector space over any field, but in this course, or for the sake of simplicity, we are going to fix our field as the set of real numbers, because most of the examples that we are going to see in this course will be based on this R field. So this is what the definition of a vector space is. Okay, so what is a vector space? So basically it is nothing but if we take a non-empty set V, okay, and we define two operations on it, call it as plus and scalar multiplication thought. For simplicity we call it as plus and dot, and these two operations on this set V must satisfy all these properties. Okay, this 1 2 3 4 5 6 7 8. So if they satisfy these properties, then we say that this combination plus dot is a vector space. And this VF, okay, so this is our set, this is the non-empty set, and this is the field. Okay, and in this course we take field as R. Yeah, so this is how we actually define a vector space, right? Now essentially what we have done is that we took some non-empty set, okay, we took its Cartesian product V cross V, and we defined two functions. First function is plus and the second function is dot, and with respect to these two functions we said that okay, these 8 properties should be satisfied. So if these 8 properties are satisfied, then we will call this structure, or this V over F with respect to plus and dot, is a vector space, and the underlying field, this F, is actually the field. Now so let us do first some examples. Okay, so we'll see these some examples so that we can have a good idea about it. So what is Rn? What is Rn? Can anyone tell me what is Rn? How do we write Rn? What is the type of element of Rn? How does the element of Rn look like? So let us start with, like, say even less. What is R2? So R2 is nothing but this R cross R, right? This A comma B. So elements are of the type A comma B, where A and B, this belongs to the real numbers, right? Similarly, what is R3? Nothing but R cross R cross R. And similarly, we can say that Rn would be nothing but we'll just take an n tuple, right? This is n tuple. So the example that I'm going to discuss is to say that if you take V as Rn, okay, then Rn over R is a vector space with respect to, now again vector space is defined with respect to some operations. What are the operation? Plus and dot. Okay, and how are we going to define this plus and dot? So define plus as plus of x comma y was what? X plus y. So in terms of Rn, what does it mean? So in terms of Rn, x is what? An n tuple, x1, x2 up to xn. Y is some y1, y2 up to yn, right? So what is x plus y? It is nothing but just the component wise addition. So we took any two elements of Rn and we defined the plus operator like this. Similarly, we defined for dot operation. So for alpha belongs to R and x belongs to Rn, so this my x will look like something like x1, x2 up to xn. So how are we going to define this alpha dot x? That is alpha dot x1, x2 up to xn. So this is defined as alpha x1, alpha x2 up to alpha xn. Right. So we took the set Rn, okay, we defined an operation plus and an operation dot, and the claim is it is a vector space. So we got the set, we got the two operations, but now to know whether it actually is a vector space or not, what do we need? We need to check all those 8 properties, right? So we are going to right now just check all these properties quickly. We'll check, okay, it is very easy and you all can actually follow. So we'll still check these properties to claim that this indeed is a vector space. So what is the first property? The first property says that x plus y is equals to y plus x. So the first property is that x plus y should be equal to y plus x. So we are going to check, right, whether it is happening or not. So this my x is something like x1, x2 up to xn. Y is something like y1, y2, yn. So what is my x plus y? x1 plus y1, x2 plus y2 up to xn plus yn. This is how we defined our plus operation, right? So see, normally the plus and dot that I have written in this definition, okay, this definition, this plus and this dot, they represent addition, okay, they are not the actual addition that we do. They are not like 2 plus 3 equals 5, right? They are not that addition of real numbers. Rather they are just functions, okay, which represent addition in some form. So for example, in case of Rn, the addition is defined like the component wise addition. For a matrix, again the addition is defined as, so for example, if we have to add two matrices, what we do is that we just add it component wise, right? So there the addition is defined on the matrices. Here the addition is defined on the set Rn. Similarly, we can define addition on functions also. So we will see that again. So now coming back to this I can actually write y1 plus x1, y2 plus x2 up to yn plus xn, right? And this I can actually write as y1, y2, yn plus x1, x2, xn. Now why I can write it this because this xi and yi, they are actually real numbers, and we know that real numbers are commutative. That is, if I take two real numbers, it doesn't matter in which order I am going to add them, right? And this is equals to y plus x. So this is how my first property is satisfied. The second property was associative. So here we have one z also, z1, z2 up to zn, and obviously we defined x as x1, x2, xn, y as y1, y2, yn. So the claim is that first I add x plus y and then I add z. This should be same as if I add first y plus z and then add x. So again this is going to be easy, because if I take this x plus y plus z, so what is x plus y? We just saw x1 plus y1, x2 plus y2 up to xn plus yn, plus z1, z2, zn. This is z, right? And now I want to do component wise addition, that is x1 plus y1 plus z1, x2 plus y2 plus z2, and xn plus yn plus zn. But this I can write as x1, x2, xn plus y1 plus z1, y2 plus z2 up to yn plus zn. Now what is this? This is my x and this is y plus z, right? So the second property is also true. Now for the third one, that it must have an identity. So what is the identity element of Rn? Can anyone tell me what is the identity element of Rn? So you guys don't know what is the identity element, or you guys are shy? If you guys are even shy, you can also type it in your chat box. That is also fine.
Sir, 0, 0 up to 0,
yeah.
0 n.
So all the elements are actually 0. Okay, so this is 0, 0, 0, 0. All the elements are 0. So now note again one thing here, that this 0 is not actually a real number, right? This is a vector. This is 0 vector, right? And that is why whenever we have to distinguish between a real number 0 and a 0 vector, so we generally what we do is that we write this 0 a bit bigger. So whenever if we are writing this 0 a bit bigger or in a more darker form, so it tells us that it is not the real number 0, but it is actually the 0 vector. Okay, then inverse. So for any x belongs to Rn, x is what? x1, x2 up to xn. So what is the inverse? The inverse is, let's say, y, and this y I can take as minus x1, minus x2 and minus xn. So now if I add x plus y, So that is, if I add component wise x1 plus minus x1, x2 plus minus x2, I am going to get 0, right? I am going to get the 0 vector. So for any x, I got this y as inverse. This y is the inverse. And then you have some more properties with respect to dot that I want you guys to verify, most probably by yourself, but still okay, fine, I'll do this also. So what is this? Alpha dot x plus y. This should be equals to alpha dot x plus alpha dot y. So whether it is happening or not, we can see that what is x plus y? It is x1 plus y1, x2 plus y2, up to xn plus yn. Now if I write it, it is alpha x1 alpha y1, alpha x2 alpha y2, up to alpha xn alpha yn, right? But this I can actually write as alpha x1 alpha x2 up to alpha xn plus alpha y1 alpha y2 alpha yn. And now I can just take the common alpha. So if I take alpha out, I will have x1 x2 xn, which is my x, and again same, if I take alpha out, I will get y, right? So this is also true. Similarly, the sixth property is alpha plus beta dot x. Now what is this? This is alpha plus beta x1, alpha plus beta x2, and alpha plus beta xn. Now I can just separate it and I can write it in different form. That is alpha x1 alpha x2 up to alpha xn plus beta x1 beta x2 up to beta xn, right? So this I got as alpha dot x plus beta dot x. Yeah, so this is also true, right? Because this is what I had to prove. I had to prove that alpha dot x, this is equals to alpha dot x plus beta dot x. Similarly, the seventh property is pretty easy, that alpha beta dot x is equals to alpha time beta dot x. So what am I going to do? That I am going to take this alpha beta and I am going to multiply it with this. I am taking the dot operation on this vector x. So how did we define? We define it like this. So whatever is the scalar, we are just going to multiply it with the vector elements. And now actually I can write alpha take common out and I will get beta x1 beta x2 up to beta xn, and this is equals to alpha beta dot x. This is also true, the seventh property. And now the eighth property and the last one is that 1 dot x. So this is again very trivial, as x1 x2 to xn. So this will be 1 dot x1 1 dot x2 up to 1 dot xn, which is equals to my x itself. Okay. So we saw that for Rn with respect to the field R, okay, we defined one plus operation, we defined this dot operation, okay, and we checked that all properties satisfy. Right? So we can say that this Rn plus dot is a vector space. So some people also write as Rn over R plus dot is a vector space. So the only difference is here that you are specifying on what field we are talking about. But for the sake of simplicity, when the field is fixed, for example, let's say we have fixed our field, so this can also work. But more general form of writing is that first you write the space, I mean the set, which is the Rn, then in bracket you write on what field we are defining the vector space, that field, and then the operations, that is plus and dot. So this proves that Rn over R is actually a vector space because it satisfied all the properties. Now let us see some more example. Okay, I can have one more example, but this time I am not going to prove all this. So let X be any non-empty set okay, and what am I going to take is that I am going to take a set V as the set of all functions such that my f is a function from x to r. Okay, so this is the collection of all the functions, right? So this V is a collection of functions. The elements of V are not any real numbers, but the elements of V are actually functions. Okay, so now again we got the set, right? Field we are talking about as R only, but again we have to define operations, my plus operation and dot operation. So how we are going to define the operation is that the plus operation is defined as we will take two elements of the V. Now the elements of V are functions, so we are taking two functions f plus g over some element x, and this will be defined as f of x plus g of x, right? Where this f and g belongs to my V, this x belongs to the capital space X on which the function is actually defined, which is the domain of the function, right? Because what is f? F is actually a function from the set x to r, so this small x is actually coming from the domain, right? So this is how we are going to define the plus operation. The dot operation is defined as, I mean, the scalar multiplication. So for the field is R, so let me just specify here. So for alpha belongs to R, which is the field, I am going to define alpha f of x is equals to alpha dot f of x, and this is how my dot operation is defined. So again what we did is that we took one set V. Okay, now this time the V is a collection of actually functions. We defined our plus to be like this, we defined our dot product to be like this. This is our plus, this is our dot product, and we will claim that this V with respect to this plus and dot is a vector space. So it satisfies all those 8 properties. I am not going to actually check all the properties again and again, but yeah, so what will be the identity in this case? What will be my 0? So this is going to be the 0 function. Okay, the 0 function, that is f of x is equals to 0 for all x. So what is going to be the identity? Identity is going to be the 0 function. Okay, so now one thing note here is that this identity actually belongs to V, right? So it should be a member of V, and it should be a member of V, and what kind of member V contains, or what kind of elements V contains? So V actually contains functions, right? So we have to take the 0 function as the identity. So here 0 is not a number or a vector, but the zero function. Okay, similarly we can define inverse. What will be the inverse? So if you have some function f of x and you want to find its inverse, so the inverse is simple. You can just take minus of f of x, and if we take, this is going to be the inverse of f. So you can check all these properties and actually confirm that it indeed is a vector space. Okay, then we can have one more example. So you guys can see it properly, right?
Yes, sir.
Yeah, fine. So there is one more example which I'm just going to mention, which is the set of all matrices of order m cross n, set of all real matrices. Okay, so whose entries are from the set R. Okay, so this is the set of all real matrices of order m cross n whose elements or whose entries are from R. Okay, and you know, with respect to usual addition and scalar multiplication, this is a vector space. So what I want to say here is that if we take all the matrices of order m cross n, okay, and if we take the usual addition, that is the component wise addition, and the scalar multiplication, that is if I have to multiply a scalar alpha to a matrix, what I do is that I multiply all the entries of the matrix by alpha. So in this way, if I take, then it is also going to satisfy all the 8 properties, and this is also a vector space. So again, I am not going to check the properties as it is a very boring and tiring work. Okay, so now actually we can have some so now we can look at some important theorems, right? So the first theorem says that if I take 0 and if I multiply it with at x, so this 0, see, now again there is a distinction, this 0 belongs to V, okay, is an element of V, right? So this 0 can be a function depending upon what V is. So we just saw that this 0 in the previous example was a function. Okay, in the matrix example it is going to be a 0 matrix. In the Rn example it was a vector whose all entries were 0, right? So this 0 actually depends on V, but the 0, the small 0 that belongs to the field, okay, or in this case R, is the real number 0. Okay, so since the notation is a bit same, so you may get confused. That is why I am specifying what is the difference between these two. So the theorem says, so the theorem is, the first theorem says that if I take 0, which is the real number, and if I multiply it, or if I take the dot product or scalar multiplication with respect to with any vector x in V, then I am always going to the 0 vector where x belongs to V, right? So this is 0 real number, right? this is a vector of V, and the result we are going to get is the 0 vector. Okay, this is not a 0 real number, this is 0 vector, and this is real number 0. So how do we prove it actually? So the proof is pretty simple, that 0 dot x, we know what is 0. 0 is equals to 0 plus 0, right? So now I can use my what property I can use? So the property I can use is the property 6. What does property 6 says? That, so I'm just going to mention here property 6, that alpha plus beta dot x is equals to alpha dot x plus beta dot x. So now in this case, this alpha and beta are real numbers, are the elements of the field. So this 0 and this 0 are also the 0 real numbers. So with this property actually I can split it, is that I can write 0 dot x plus 0 dot x, right? Now these elements, this 0 dot x, they actually belongs to the vector, right? Because if I multiply 0 with a vector, then I'll get a vector. I do not get a real number 0. What I'm trying to say is this, that if I do 0 into 1 comma 2, I get 0 comma 0, right? I'm getting a vector. So this belongs to my R2. This is not the real number 0. So this 0 dot x and this 0 dot x are actually are elements of V. So now since they are elements of V, so with property 4, that any element of V will have its inverse, right? So with this 0 dot x has inverse, and we define it as, or we denote it as minus of 0 dot x. So now if I add this minus 0 dot x to both the sides, so I had 0 dot x plus, now I am going to add this minus 0 dot x and here I had 0 dot x, 0 dot x plus minus of 0 dot x. What do I get? So I am adding a vector with its inverse. So what I get? I get the 0 vector. So V here I am writing in term to denote that it is actually a vector, or I can just write it as a big 0, okay, to denote. Again here I will get 0 dot x, and this is again the 0 vector. This is the 0 vector or the identity element, right? Now if we know that if you add it to if you add anything to the 0 vector, you always get that element back, that is x plus 0 is equals to x. Okay, so this x here is 0 dot x, which belongs to my vector. So I got as 0 is 0 dot x. Okay, so this 0 is a vector and this is the real number 0, right? And this is what we had to prove. So this is what we had to prove for all x, right? So we just proved it. So the notations are a bit complicated maybe for the first time, because in both cases we write 0, but one thing to note here is that this 0 is actually a real number, whether this 0, it is the 0th element or the identity element of the space V, right? The second theorem says that uniqueness of identity unique identity. That is, every vector space has a unique identity. So to prove it, we can assume that, let's say, the vector space V has two identity elements. Zero and 0 dash. Okay, so now, as 0 is the identity and 0 dash is some element of V, so we have taken that both of these 0 and 0 dash are actually identity elements. So for the first case, I am considering that, okay, 0 is my identity and 0 dash belongs to V, that I am treating 0 dash as some element of the vector space V. So in that case, what happens is that 0 plus 0 dash would be equals to 0 dash, because we know that if you take 0 vector and if you add any vector V, you always get the vector x, right? So you have taken any vector x here from the vector space V, and if you add it with the 0 vector, you always get that vector V, which is the third property. So applying the third property, we got this. Now again, take 0 dash as the identity and 0 belongs to V. Now since 0 dash is again an identity and 0 is some element of V, so I can play this game again. So what I'll do is that I'll take, okay, that 0 dash plus 0 this time is going to be my 0, right? Because 0 dash is the identity here. So 0 dot x is going to be my x, and here I have taken x is equals to 0. So this is also okay, so yeah, fine. So this is also with property 3, right? This also is given by property 3, and this is also equals to 0 plus 0 dash. So what we do is that we take this equation 1 and this equation 2, we call it a 2. So 1 and 2 implies 0 equals 0 dash, and this proves that identity is unique. Okay, then the third one is the inverse, that additive inverse is unique. So to say that any, so this is the third theorem, okay, that any vector space, okay, has a unique inverse for every element x. So again, let's say we prove it. So let x is my some element of V, and we take two inverses, y1 and y2. Okay, so now since y1 is the inverse of x, what does it imply? It implies that x plus y1 is going to be the 0 vector is equals to y1 plus x. This is by definition of the inverse. Again, since y2 is the inverse of x, so the same property y2 will also satisfy, that is x plus y2 is equals to 0 is equals to y2 plus x, right? Now what we do is that we take this sum. Now we take this. So x plus y1 is 0. Okay, from here we can see that x plus y1 is 0. I will add y to both the sides. So y2 plus x plus y1 is equals to y2 plus 0. Okay, adding y2 both sides. But we know that it is a vector space, and actually this operation plus is associative. That it means that I can also write it as like this, and y2 plus 0 is going to be y2, right? So this is by the associativity property. And now since y2 was the inverse of x, so this portion is actually 0. So 0 plus y1 is equals to y2, and we got y1 equals y2, right? So this is what we wanted to prove. Okay, so now there are some more theorems which I want you guys to try yourself. So they are given in the book Linear Algebra with S. Kumaresan. So S. Kumaresan. Okay, I want you guys to try them. Okay, so see, I'll give you exercises, not because I am lazy, but I want you guys to try, because you can understand only if you try, right? And I'll be providing you all the solutions. So whatever exercise I'll give, most of the exercises I will provide you with some solutions. So that is, the theorem is that minus 1 dot x is equals to minus x, such that x plus minus x equals to 0 for all x. So this is one theorem. The another one is that alpha dot 0 is actually 0. So now see, this alpha belongs to R, and this 0 actually belongs to the vector v. So this is the big 0, that is the 0 vector, and not the real number 0, right? And the sixth property, this is for all alpha belongs to R, and the sixth property is that alpha dot x is equals to 0 for any alpha belongs to R and x belongs to v. That implies either alpha is equals to 0 or x is equals to 0. Okay, so I want you guys to try these things, these three. I'll provide you the solutions. I'll give you the handwritten notes, or I'll give you some video in which I'll explain these theorems as well. But I want you guys to try it for once, right? So okay, so I think we can finish it for today.